Cool, thanks. Hey everybody, so apologies for the people who might have been at EclipseCon North America. Phosphor-G, as this talk is very similar to the talk that Jesse gave then. I had grand aspirations to update and have it be much more platform focused, which is what we're really working on next, is building much more of a geospatial platform for satellite imagery. But this skews a bit more towards the space side, but space is cool, so it should still be pretty fun. So the last 20 years has seen this explosion of information available at our fingertips. Technologies like Wikipedia, the internet, provide this amazing access to information, but information about our planet remains remarkably opaque. So this is a picture from the Apollo 17 astronauts as they were hurtling towards the moon, and it kind of kicked off this environmental movement of just seeing like our fragile planet. But like, you can't really get much out of this. Like, it's an interesting picture, but kind of extracting information out of it is not really there. Now, we've made a lot of progress. You can have images of the Earth in your phone, like satellite imagery in everyone's pocket, but those snapshots still can be years old. What you really want is something that captures the world changing every day. Seeing these like changes in snow cover, this is from the Suomi satellite over the span of a week. But you're still very kind of low resolution. You ideally want to see human change and that human impact. This, you can see some environmental change, but being able to get higher resolution gives you this kind of unprecedented ability to actually act on change. So the core of the thing is we have these huge satellites, and that first picture was from a satellite that was capturing a whole lot, but you couldn't really zoom in. And basically with these really big satellites, you have to choose between either global coverage at a very low resolution or high resolution but with very low coverage. So there's amazing satellites that can get 30 centimeter, 20 centimeter images, but you're through just a very narrow hole, so you have to pick where you want. So the Planet Labs approach is to build very small satellites and a whole lot of them. So instead of just 3, 4, 5 satellites, build hundreds of them. And you can think of this similar to like computing, where there were big supercomputers, and that was kind of the way of doing things, but then Google and Amazon are about taking all these very small computers and hooking them together into a much more powerful thing. So what others are doing in the satellite imagery now is this sort of tasking, where you're doing point and shoot operations, and you get these pretty limited observations. You miss serendipitous events. You have to know, I want to take a picture here. And you kind of need a human in the loop figuring out where are we going to point this thing, what's important. The Planet approach is have enough satellites to capture an image everywhere. So as you can see, this is the kind of operations is each one of those dots is a satellite, and as one passes over a place and the Earth kind of rotates beneath it, the next one follows it right in place. So it lets us create this sort of daily snapshot of the Earth without any gaps. So this leads to some cool things, as kind of like always on monitoring. So it's really about this monitoring mission, getting fresh and persistent data, and also being able to kind of rewind. And there's kind of this metaphor of like, if you're working with software, when something breaks, the first thing you want to do is kind of see what happened and rewind back to see that. You want to do that with a disaster and kind of see what was it like the day before and what occurred. You also, as an example of sort of deforestation, right now with kind of an image every 16 days, you can do lots of work to figure out deforestation and like, oh, this forest is going away, that's bad. With you're getting a daily shot, then you can actually do something about it. You can be like, there are people cutting down this tree, let's go stop them. So yeah, what we're really about is the kind of change. This is an image caught on Landsat, and the next day we caught this, where you could see the field burning. You could see some harvesting being done. Another example is kind of like soybean fields, But the key in this is to start to extract out the information. So it's not just, oh, that was a cool change. It was, what's the information that comes out of how many acres were actually harvested there. So that's kind of really what we're going for. In terms of our approach, so yeah, existing satellites, are an amazing invention, but there's very few of them. And they cost hundreds of millions, if not billions of dollars. They require tons of upfront planning. I mean, it's like 5-10 years to build one of these, many years to complete, and they're not really sort of repeatable. For those us in the software world, like this kind of sounds familiar. Like this is how software used to be built, this kind of cathedral approach. Eric Raymond wrote on this with the cathedral and the bazaar, where the contrast in the way software was built and the early days of GNU relative to Linus Torvald and Linux. So it was this bazaar approach and less kind of upfront planning and moving much more agilely. So this brought us Linux and Apache and Django and many sort of open source projects. So at the core of Planet Labs was kind of taking these ideas from software and working much more like a software company as opposed to a traditional aerospace hardware company. So the founders were all at NASA and all working on missions. One of them was working in headquarters, but they were all a bit frustrated with kind of how slow things went. So they started thinking like software people. And the first thing they did was this minimum viable product that was called PhoneSat. And it's literally a Nexus 1 strapped to the bottom of that cube. The antenna is like a piece of measuring tape. And they just kind of slap the components on. The cool thing about it is like in a phone, I mean, the realization was that this has pretty much all the major parts needed to be a satellite. It has a faster CPU and more memory than most satellites on orbit, multiple cameras, multiple acceleration and rotation sensors, a compass, a GPS receiver, radios, battery, all of which have had this huge investment from the consumer electronics industry. Like trillions of dollars go into this, whereas space, everything is built from scratch and custom engineered. So then they did another very Silicon Valley thing. They started a company in a garage. This is them in the early days, raised some money. And the first satellite they built was all with off-the-shelf parts. So using commodity electronics from the telescope to the sort of rebar, like the brains was an Intel system on chip running Linux. And they launched it and managed to get a picture down. This was April 21st, 2013, and was really kind of incredible, like that they actually got a picture from space. Now, was this like super high quality? Could they repeat this a whole lot? Maybe not, but they could put this in front of investors and show that they had something that worked and get it better and better. So they've been really going this sort of agile aerospace approach using sprint boards and agile planning and have done, I guess now it's 13 generations of satellites over the past kind of 3-4 years. A lot of the philosophy is, yeah, kind of release early and often, not testing a whole bunch on the ground, but it's enabled by this frequent access to space. So I think we've been on 10 or 11 launches at this point. Yeah, we actually like start to lose track. We've launched 101 satellites, but yeah, it's just kind of like the shift to thinking of them as like cattle instead of steer. Like just like you fire up a virtual machine now, you no longer name your server like they did 10 years ago. Similar to satellites, like they don't have an individual identity. So for launch, we have this kind of funny tradition of cooking pancakes. This made sense with the first launches because they were like afternoon East Coast time and it was the morning the West Coast time, but now launches happen at all different times and we'll still have pancakes at like 5 p.m. or sometimes they're at 2 in the morning and people come in and make pancakes. But yeah, launch is a pretty exciting time. And this was one of our launches that was really cool. So we make the satellites, we design, build them. We don't actually build the rocket, so we just catch a ride with someone else. This one was kind of packed full of a whole bunch of technology. Like, we were really excited about it. But yeah, sometimes the launches aren't always successful. So that was a little bit of a sad day. This was the reaction of the crowd to this happening like in real time. You can actually see the fireball in the background as we like watched our hard work kind of go up in flames. And yeah, I think there were over 24 satellites aboard, and we actually had them trying to get in touch with us, like blinking from the beach. Like we actually recovered them kind of amazingly, and they're actually now back in the lab. Like they were scraped up with sand, but still mostly intact. But the cool thing, you know, for anybody else, this would have been a kind of company-ending event. For us, it was kind of a validation of our approach to this Agile Aerospace. So like lots of tech was packed onto those, but basically we took all the tech on those 28 satellites and put that onto 2 satellites that we built in 9 days. And we kind of had the parts on hand. We put a near IR telescope on one, we put a much bigger telescope on the other. And yeah, we had to build them and ship them in 9 days to go on the next SpaceX flight. So yeah, it was a pretty exciting thing, and you know, and yeah, since then we actually had another blow up, which was a little sad, but you know, they're kind of just minor setbacks since we're tend to get in space every 3 months. So a lot of the launches we do actually go to the International Space Station. So these are our satellites being pushed out from the space station. Yeah, I love some of these shots. Like you can just see the Earth behind it as they sort of fall into the abyss, but then that's really what an orbit is and kind of rotate through. But yeah, most people who launch satellites don't get to see their satellites. But yeah, the International Space Station has been this great kind of frequent access to space. Like it's sort of refueled every 3 months, and we try to most always get some satellites going to test the latest technology. So yeah, building this many satellites has really required kind of new approaches to space. So taking learnings from manufacturing, open source, web operations. We're kind of taking satellites out of the clean room and onto developers' desks. So this little box of boards right here is what we call a box sat. And so that's like all the hardware needed to kind of run and debug the onboard software for the satellite. And so he can just do these much faster build, run, test cycles and put it, once he gets it working, then we can just deploy it to the satellites that are already in space. So yeah, we do some fun things of like finishing the hardware, but not even quite finishing the software, because some of the satellites we have to ship like far before they're there. So we put like an FPGA to do JPEG 2000 compression on board, which is pretty awesome because it lets us take like much bigger pictures. But yeah, they were like, just sending it up to space. I think somebody recently asked me, was like, is there any danger of bricking the satellites? And usually there's not, but there was something about what they were doing with the JPEG 2000 FPGA stuff where they're like I was talking to the engineer, he's like, yeah, I was like a little nervous about bricking it. So we have not bricked a satellite in space yet, and it's not that likely. But there are some operations they do that have that potential. Another pretty cool improvement is, yeah, these like iterations in space. So there's this thing called time delay and integration, which has been used in aerial reconnaissance, where basically you leave the shutter open for longer to gather more photons, and then you just move it. It's like moving over the Earth, and you kind of collect the light at the same speed it's moving. So we're doing this from space, where the same speed that we're kind of hurtling over things, we're collecting more and more photons in there, and it lets you gather more light and more signal and get kind of higher quality. So our camera manufacturer actually told us that it wasn't possible with the camera, but it's like most CCDs can handle it, and we like looked in the manual and like hacked the firmware and showed it to them. They're like, oh, I guess you can. So we're up to, I guess this is just 6. You can kind of see the quality improvements, but we're up to like 12 lines of TDI now, and can possibly go more. You just have to stay really stable, because if you're moving a bit, then it kind of blurs. Yeah, so operation of satellites can be resource intensive. This is mission control of a sort of traditional satellite, but operating hundreds of satellites really kind of requires automation. We couldn't have like rooms full of people for every satellite. So this is our mission control. It's kind of like 2 developers hiking on Python. In this, the screens are actually sort of on, yeah, but they tend to only really be on when like the media is there. Like for the most part, people don't use them. Like they're just at their computer and figuring out what to do. But it's all about sort of anomaly detection and fixing the kind of systemic problems. It's not like steering them, and it's figuring out these algorithms that will actually keep the human out of the loop, but kind of optimize for like avoiding clouds. Like there's a lot of clouds in the world, like, and we don't want to take pictures of them, and optimizing for places that we haven't taken a picture, putting priorities into that. So there's a whole like, I think the first version was like genetic algorithms, but I mean, it's kind of this crazy problem of you have, you know, tens up to hundreds of satellites, you have 20 ground stations, you have many passes, and you need to figure out like which should talk to which at what time and what instructions should give up. So it's, yeah, a bunch of kind of cool optimization problems. But yeah, our mission control is powered by Django, RapidMQ, PostgreSQL, Cesium, front end. So yeah, a lot of open source software through our mix. Our ground stations are basically Linux servers with huge antennas. We build our own ground stations. I think we have about 20 of them now. And then, yeah, we have an artist who will often decorate the ground stations with cool designs. And then, yeah, all of this is to go at this sort of like Earth imaging as a service. So like make the images available. We're not selling satellites. We're not selling the capability. We're kind of selling that end product. So that's a lot of where I come in. This is a fresh cloud, and we take a lot of pictures of clouds. Actually, much less now. We used to take, 55% of the Earth at any given time is covered with clouds. Yeah, a lot of people at Planet kind of hate clouds now, like especially on those like sparsely cloudy days, you know, where it's like sunny, but then you look up and there's clouds because like it's just getting in the way of our pictures. Yeah, our approach to kind of processing everything is also heavily cloud dependent, a different cloud. But yeah, we do a lot of spot instances. I think we're probably running like 4,000 virtual machines at once in kind of a job system to kind of process all the imagery. And make it available. This is a little video we did, which is actually going at the speed that the satellites travel through space. So taking a picture each time and then kind of combining them. So eventually we'll probably use our own base map as a source of truth. Right now we're doing feature points extracted from Landsat to kind of spatially rectify. We go from a raw and then need to figure out kind of where it is on the map. So pull out like what are the actual points and then be able to geo-rectify and ortho-rectify against a DEM. This has been some kind of interesting problems, like our initial satellites in this kind of agile approach knew much less where they actually are. So they'll tell you, oh yeah, I think it's here, but usually most all the rectification algorithms are built for, you know, being off by like 500 meters, like kilometer. Some of ours would be off by like 100 kilometers. So we had to do like computer vision area searches to kind of get around that. But yeah, the satellites are getting much better, and we also have figured out sort of how to do the rectification wherever it is. And yeah, the goal is to kind of pull down imagery as fast as possible. Usually before I give a talk, like an hour or two before I have time to like download an image. There's no Wi-Fi here, so I couldn't do that. But we're kind of flowing images throughout, putting it through this whole pipeline. So aiming to get images to people's hands in less than 24 hours. Right now, for some of them, if the passes are right, we'll see an image an hour or two after it's taken. And then you're able to put it through the whole pipeline on this kind of massively scalable cloud system to do all the processing and rectification and make it available on the web. So one thing we're doing is kind of considering mosaics as a core competency. So instead of making people work with the image and put it together themselves, we're kind of automatically doing it, be able to kind of take out clouds and put that together into one mosaic. And then, yeah, we're using this kind of best pixel methodology. This is actually what Frank Warmerdam is at Planet. He's the author of GDAL, and this is a lot of his work. So divide it into a grid and kind of pull those images into a mosaic that we can serve up as web tiles as opposed to a bunch of just individual images. Is this working? It didn't really work. Link starts to work. Anyways, it's just showing going into Mosaic and then viewing the scenes that are behind it. So, you know, a Mosaic from Google or Mapbox might be 2 months old, it might be 2 years old, but you have no way of knowing that. So key to us is this kind of traceability to be able to go back to, you know, what exactly what picture went into it, and then be able to take a slice of time and say, just show me images from the last week. Even if that's kind of sparse, I know that every pixel came from that week. This is an example of us doing the same technique with Landsat, just kind of automatically compositing it together. And then everything's available through REST APIs with JSON, GeoJSON, so kind of make it truly programmer accessible. And then on top of that, I think none of these working. That one sort of works. So on top of that, we're building these Gooeys to help people find images. And yeah, we're making the Gooeys fully built on the APIs, so anybody can build a similar thing. We're not doing kind of anything special on our side. And then playing a lot with what does this look like over time, and lots more to do here to kind of really display that stuff. But yeah, working to actually load it quickly in the browser and get this imagery available to people like as quickly as possible. Oh yeah, and then starting to do notifications, so you're able to kind of register an area and say, I care about this, and send me an email when there's a new image there. And then that's kind of the basis of things like change detection, instead of saying, oh, every time we get an image, especially since next year we're launching enough to get an image every single day. An email in your inbox every day that you took a picture is less interesting, but start to email like, oh, like this changed, so you should check out this image. So that's a lot of where we're sort of looking to go. And then key to us is like making this a flexible platform. And this is an example of an app that's built on top of that same platform with another set of tools. And you're able to kind of see the latest image, slide it back and forth relative to a base image. You can add any image to us. You can kind of mark up the image with something you want. And that's our kind of next step, is have this solid base of serving the imagery on the web, be able to get that to anyone, but then have this much bigger ecosystem of people kind of customizing and making apps that are relevant to domain and you know, doing things on top of satellite imagery. And that's kind of this core thing of what does it mean for satellite imagery to be truly online, which like wasn't really possible even 5 years ago. Which yeah, leads to another cool thing, which is we recently acquired a company called Blackbridge, which had acquired a company called RapidEye that operates 5 satellites and has a 6-year archive of information. So we're putting all their information, I think it's a few petabytes, available online, accessible in Amazon through APIs to sort of everyone. And then yeah, we're looking to kind of try to do open as much as possible. It's still early days for us. Our gallery is all Creative Commons licensed, and then we just announced this Open California initiative where we're taking all of our data that's gathered from the RapidEye and planet constellations, as well as 2 years of historical archive in California, and putting it all available under a Creative Commons license. So really kind of want to encourage people to do new algorithms, really good in change detection, you know, what's kind of possible when there's much, much more satellite imagery than has been available before. And then that's linked to our first release of our platform beta, where users can get at that. We're looking to do open source. We help maintain projects like GDAL and OpenLayers. Some of our algorithms for compositing and rectification in the post-processing chain have been open sourced and hoping to do a lot more. And it's kind of a cool dynamic where really at heart we're a data company. So yeah, I mean, the founders definitely aspire to the point where all our data can be open, but that's probably 4 or 5 years away to figure out the next business model when pixels start to get commoditized. But as a data company, doing more and more software open is easier to do. Yeah, and I mentioned the Artisan Residence program, which is definitely a cool thing of kind of how much art permeates what we do. And yeah, I recently launched this Explorers program that actually we launched it a while ago, but now we're actually inviting people in where we had not been before. And so, yeah, I encourage all you to sign up. Yeah, I think anyone who marks that they're a developer gets invited in a week, so that's kind of the quick trick to actually get invited. A lot of it is that Our tools are still more API focused. In a couple months, we'll have the RapidEye data in the Gooeys, and then we'll start to invite everyone. So yeah, I encourage you to apply, and yeah, if you don't get in right away, just shoot me an email, and we're super psyched for more people to do more stuff on our platform. And that's all I got.